Welcome to our fourth lab for Physics 2211, oscillations. The purpose of this lab is to investigate a mass spring system by comparing a real spring with a VPython simulation. The study examines both the motion of the mass and the system's energy changes. By recording kinetic potential and total energies, we test energy conservation and evaluate how well the model predicts the real system's behavior. For the models and fundamental physical principles, we have a VPython model which simulates a mass connected to a spring, accounting for spring and gravitational forces. It is based on Hooke's law and Newton's second law, and it also tracks kinetic potential and total energies of the system. And this allows the simulation to replicate both the motion and energy behavior of the real spring mass system, enabling direct comparison with experimental results. As a preview of the main result, the lab showed that the motion of a spring mass system can be predicted by accounting for all forces, and that small initial errors, however, accumulate over time, causing the experimental and model data to diverge slightly and diverge more as time passes. For the main physics ideas, in this lab, the motion and energy of a mass spring system were analyzed using fundamental physics concepts, Newton's second law, calculated acceleration from the net force, including gravity and spring force, and velocity was updated using the given formula. The momentum principle described the mass's response, while the energy principle tracked changes in kinetic, gravitational, and spring potential energies, and calculating the total work that way. And the VPython model used force-based updates for motion, and the energy principle guided experimental energy analysis. For the initial conditions, the system consists of a mass attached to a spring fixed at the origin, with gravity acting as a constant external force, which is the system. The system is the Earth. The mass starts at x equals negative 0.1294 meters and y equals negative 0.6635 meters at rest, with a mass of 0.402 kilograms. The spring has a relaxed length of 0.188 meters and a spring constant of 7.3 newtons per meter. This value set the initial displacement and forces, and energies are initialized with zero kinetic energy, gravitational potential energy based on vertical position, and spring potential based on the initial stretch, providing the starting point for updating motion and energy throughout the simulation. For the details of the experiment in the simulation, each loop iteration updated the mass spring system's motion and energy. Gravitational and spring forces were recalculated at every step, and Newton's second law was used to update velocity, which in turn updated position. Kinetic, gravitational, and spring potential energies, as well as total energy, were calculated and recorded at each step. The x and y positions were tracked throughout, allowing direct comparison with the tracker data. And this iterative process provided a step-by-step prediction of motion and energy, showing how the model evolves over time. After the experiment, we found that at the beginning of the experiment, the experiment data closely matched. However, because the forces in the system are not non-constant, small differences in initial conditions and measurements accumulated over time, causing the simulated and experimental positions to diverge. So over a long period, these discrepancies would continue to grow, illustrating how even small errors can lead to significant differences in systems where the forces vary continuously. So the VPython simulation initially matched the experimental motion and energy of the mass spring system, showing that Newton's second law and Hooke's law described the system very well. But over time, small differences in initial conditions and measurements caused the model and experiment to diverge, highlighting how non-constant forces amplify errors. Some possible sources of error include imprecise tracking of the mass's position, slight variations in the spring properties, and time inaccuracies, and air resistance, which is not included in the simulation but slightly slows the real mass. But despite these limitations, the experiment confirmed general trends in motion and energy, demonstrating the usefulness of computational models for predicting real-world behavior. Finally, for the what-if questions, for the first what-if question, the answer is, for the model system, the energy principle is approximately satisfied. The plots of the kinetic, gravitational, and spring potential energies show that while individual energies fluctuate as the mass moves, the total energy remains nearly constant throughout the simulation, and small variations in total energy are due to numerical errors from the iterative calculation. But overall, the model demonstrates that energy is conserved when only gravity and the spring force act on the mass. And for the second what-if question, using tracker data, the oscillation period was estimated for successive peaks in the x and y positions. The x data gave about 0.42 seconds, and the y data gave about 0.43 seconds. The close agreement shows consistency in the motion along the spring's axis, and small differences likely come from measurement noise or like slight of axis motion or something. And in conclusion, the lab showed that VPython and Newton's second law can predict the motion and energy of a mass spring system. The simulation matched the initial oscillation and energy changes, though small measurement differences and non-constant forces caused divergence over time. Energy trends were generally conserved, and oscillation periods from x and y data were consistent. The experiment demonstrates the value of computational models while highlighting the need for precise measurements and accounting for errors like air resistance and spring variations. Thank you.